Now let us look at the first sampling algorithm, which is also known as the rejection sampling algorithm. This is a very simple form of Monte Carlo sampling. Now suppose that we wish to sample from a distribution of P of z, where direct sampling is very difficult. In Python or in C++, we know that we can easily call the rand function, which will allow us to draw samples from a uniform distribution, or even the rand function that will allow us to draw samples from the normal distribution. But there won't be any available function given by your favorite compiler that would allow you to draw sample directly from a very complicated distribution such as PZ in this example. And so furthermore, if we suppose that we are unable to easily evaluate the PZ due to some unknown normalizing constants of ZP, this is the partition function, or it could be a normalizing constant in the case of our Bayes rule that we have seen in the earlier slide as given by this equation over here. Let us denote this distribution that we wish to draw a sample from equals to the unnormalized form, which we denote as P tilde Z, divided by the normalizer constant, which we denote as ZP here, where P tilde can be readily evaluated, but not in the case of this ZP here. In the case of the posterior distribution of xy, we saw by evaluating this using the Bayes rule. This is an example where the unnormalized version of this can be easily computed from the likelihood function as well as the prior probability, but the normalizer here, it involves the marginalization over all the random variable of x over p of y x and the prior probability of x dx over here. So this normalizer, which we denote as ZP, would be difficult to evaluate. This is one of the example where we want to make use of the rejection sampling algorithm to evaluate this posterior probability distribution. So here's the algorithm of the rejection sampling. Our target is to draw n number of samples from the target distribution, denoted by this red curve over here. Suppose that this red curve denotes P tilde Z, the unnormalized version of the target distribution. We'll first draw a sample from an easier distribution, which we know how to draw a sample from. So in this case, we'll call this our proposal distribution. Our proposal distribution in contrast with the target distribution, which is the distribution that we wish to model, we wish to draw sample from. So in this case here, P tilde is our target distribution and Q would be our proposal distribution, which is an easier distribution to draw sample from. So, in this case, it would be a Gaussian distribution. We can easily call the function of rand n in our favorite compiler to draw a sample under the Gaussian distribution. Now, in the first iteration, let's draw first sample from the proposal distribution Q of Z, and then we'll also draw another sample which we denote as U from a uniform distribution. We can also easily draw this sample within the range of 0 to 1 from a uniform distribution by running the rand function in our favorite compiler. We'll then do this comparison if U, which is between 0 and 1, is lesser than the unnormalized probability distribution evaluated under the sample of Z that we have drawn earlier on from the proposal distribution, divided by a K, which is a scalar constant, multiplied by the probability value of the target distribution evaluated at the sample of Zi. This corresponds to, let's say, the sample that we have drawn from the proposal distribution is Z0, and we'll evaluate this particular guy over here, this particular value under P tilde Z0, as well as we'll evaluate this value over here, which is given by K multiplied by Q of Z0, and We will then divide these two values and compare it with u. If u is smaller than the division of these two numbers, then we'll accept zi, the sample that is drawn, and increment the counter by 1. Otherwise, we'll reject this sample of zi. So what we are looking at would be the area under this particular curve over here. So since we are computing the ratio, what this means is if u that is drawn is anywhere in this white region over here, then we are going to accept this particular sample. But if it is beyond this white region into the gray region over here, then we are going to reject this particular sample. We'll do this until convergence, until we have finally found n number of samples that satisfy this criteria of the rejection sampling. So one problem of the rejection sampling is that it's not always possible to bound this particular target distribution with proposer distribution, as what we have seen earlier, that we need to select the proposer distribution such that it covers or it bounds the whole region of our target distribution in order for this check to be valid, because we need these gray regions in order for the rejection sampling to work. So in contrast, if we were to choose proposer distribution, that means that the scale of this k multiplied by the proposer distribution, which is a Gaussian distribution in this example over here, is too small, then we'll see that we'll never fulfill this particular criteria over here, and we need it to cover the whole region of our target distribution. But this is unfortunately not always possible to cover it over the whole space of z, the random variable z. So one particular way to overcome this would be, why not let's choose k to be a huge number, and we are always guaranteed that the proposer distribution multiplied by k will cover or will bound our whole target distribution. So we can choose this guy over here, kq of z, to be a very large value such that it will cover everything for sure. But this is also not reasonable. Recall that the gray regions where we will reject the samples, all the samples of z that is drawn from the proposer distribution. So in the case where k becomes too large, this means that the gray region here will also be consequently large as well. And what this means is that there will be a very small chance that we will accept the sample that is drawn under the proposer distribution. And this means that the algorithm, the rejection sampling algorithm, will never terminate. And this makes it impractical for high dimensional space scenarios. Now we'll see an alternative to the rejection sampling, which is called the importance sampling. So in this importance sampling, in contrast to rejection sampling, which rejects some of the samples and keep some of the other samples, we'll accept all the samples that is being drawn from the proposer distribution, but we'll weigh them with what we call the importance weight. And as well as in addition to the samples that it can be drawn from the target distribution, the importance sampling algorithm is also a framework for approximating expectations of a function with respect to the probability distribution. And we'll see how we can do this by drawing the samples from the proposer distribution to approximate the target distribution. We'll first express the expectation in the form of a finite sum over the samples drawn from the target distribution P of z, weighted by the distribution, or weighted by the ratio of the target distribution divided by the proposer distribution. Here we'll write this expectation over the function of f equals to the integral of f multiplied by p, and this is equals to the integral of f multiplied by p divided by q multiplied by q. So we'll make use of the trick that q divided by q equals to 1 over here to introduce the proposer distribution into the expectation of the function of f. And we know from the law of large number that this particular integration here, the integral to compute the expectation, can be approximated by L number of samples that is drawn from the proposal distribution in this case. So we'll rewrite this integral sign into the summation sign over L samples, where we can see that this guy over here, the function which we are interested over here, remains in this case, and then we are going to group this ratio of P over Q together with the function that we are interested in evaluating, and hence we will see that this ratio over here appears on the summation sign, and we are going to evaluate these terms over here over the proposal distribution, which is denoted by Q over here, where the sample of ZL are drawn from this proposal distribution of Q, and this is given by the law of large number that we have seen in the previous slide. And the quantities of the ratio of the target distribution divided by the proposal distribution, which we will denote as RL, are known as the importance weight. So from the expectation equation that we have seen earlier, we can see that this over here, which we denote as RL, it's now can be treated as a weight to the function that we are going to evaluate under the expectation, and hence this is also known as the importance weights. And the intuition behind this is that they correct the bias introduced by the sampling from the wrong distribution, because what we are after is our target distribution of P of Z here, but what we are sampling from is our proposal distribution of Q of Z here. So what we are doing here is that we are making use of this importance weight over here to tell us the difference or the bias that we have of the probability. So suppose that we are given a sample of ZL, we are going to compute this probability over P as well as Q, and then we are going to use the ratio over here to correct this particular bias, which means that this particular gap over here, we are going to correct it. And unlike the rejection sampling, as I've mentioned, that we do not discard any of the samples that is drawn from the proposal distribution in the importance sampling algorithm. So the importance weight that we've seen in the previous slide, which is given by the ratio of PZ over QZ, where Z here is a sample, the L sample, drawn under the proposal distribution of Q. And we will use this to weigh the, we'll write this as RL. We'll use this importance weight to weigh the expectation computation. But one problem here is that since we do not know this particular target distribution, which, as I've mentioned many times, that this could be a very complicated distribution due to the integral sign that is needed, we won't be able to compute this particular importance weight that is needed in our importance sampling to compute the expectation. But often we saw also in the previous slides that the unnormalized version of this target distribution, which we denote as P tilde, can be easily evaluated. So this example, we have seen it several times, where the exact target distribution of PZ could be probability distribution that we can compute using the Bayes rule. So we can denote this as a PZ tilde, the numerator, which is the likelihood multiplied by the prior divided by the normalizer over here. And this normalizer is actually the integration over PZ and X dx over here. And we say that this integration is intractable to compute. But the numerator here would be something that we can actually compute easily. And so let us also define the proposal distribution in a similar form. That is, Q of Z would be equals to the unnormalized form of Q, which we denote as Q tilde, divided by a normalizer constant, which is denoted as Z of Q over here, we then have the expectation over the function on the probability of P given by this particular expression over here, where we simply introduce the normalized form of P as well as the normalized and unnormalized form of the proposal distribution of Q. And we'll do the same trick where Q over here, since we have ZQ divided by Q tilde, which is equals to Q, and we'll introduce another Q here where they cancel out to be equals to 1. So we'll factorize out the normalizer ZQ as well as ZP to the outside the integral sign, and we can see that this form over here can be re-expressed into the summation over the L number of samples that we draw under our proposal distribution of Q, and we'll group this all together as our function. Hence we can see that there's this particular term over here, and this would be the expectation of F under the unnormalized form of the proposal as well as the target distribution, where we simply write R tilde as our importance weight. Now the next thing that we need to evaluate would be the ratio of the normalizer ZP over ZQ, with the result of this guy over here, ZP over ZQ equals to 1 over Q of the integral of the unnormalized target probability distribution. Since we know that PZ is simply given by P tilde Z divided by the normalizer, which is equals to the integral of P tilde Z over Z, and this term here would be equivalent to PZ, which is this guy over here. The next thing that we can do would be to replace ZQ over here with Q and Q tilde, since we know QZ equals to Q tilde Z divided by ZQ. We can simply rewrite ZQ to be equals to Q tilde Z over Q of Z and replace it into the integral equation over here, and then we'll end up with this particular form where we'll simply use the law of large number to approximate this integral sign with the summation sign over the function that we're interested in, which is this guy over here. And now we'll represent this particular function with RL tilde. Now we can substitute this back into the expectation equation that we have seen in the previous slide over here. So we'll substitute the expression back over here, and this is what we are going to get, where the expectation is now given by the importance sampling weight multiplied by the function that we are interested in, where W over here is simply given by R tilde divided by summation of R tilde. Well, we can see that now the importance weight can be easily computed from the unnormalized form of the target distribution as well as the proposal distribution of Q. Here's the evaluation where we can put this particular expression back into the expectation term to get this final expression over here. Now there's also some limitations of the importance sampling algorithm. The success of the algorithm depends critically on how well the target distribution matches the proposal distribution, and strongly varying P multiplied by F has a significant proportion of the mass concentrated over small regions of the Z space. So what this means is that the set of importance weight may be dominated by a few weights having large value and the remaining being insignificant. So an example here would be in the case where we have a target distribution that looks something like this. It might be a multimodal distribution, and then what we have for a proposal distribution could be something like this, where we say that this is our proposal distribution, and we can see that there is a severe mismatch between our proposal distribution and our target distribution. And what will happen here would be that we'll always end up trying to draw samples at the high probability of our proposal distribution here, where we will end up trying to get some important weights over this particular region where there is a high probability for our proposal distribution, and these importance weights over here would always end up to be very low. So we'll only end up with a very few samples in contrast over here, which corresponds to low proposal distribution probability, but over here we'll get very high importance weight. But what we'll get here would be a significantly sparser distribution of the samples that we can draw from, because it corresponds to a very low probability region of the proposal distribution. And as a result, we can see that once there is a significant mismatch between the proposal distribution and the target distribution, the end results of the samples that is being drawn from the proposal distribution will not be a very good representation of our target distribution. Nonetheless, let's go through an example of how importance sampling can be applied on the Bayesian network. Suppose that we are given this Bayesian network which consists of 5 random variables denoted by x1 to x5, and here's all the conditional probability that is given to denote this particular Bayesian network. And the question is that how can we compute the marginal probability or the conditional probability of x1 for 5 condition that upon that x2 equals to 1 and x3 equals to 1. So obviously we know from our previous lecture that this can be easily computed by using the sum product algorithm or the message passing algorithm, but let's just look at this example, simple example over here, and pretend that this particular marginal probability or conditional probability is a very complicated one that we have no way to compute it, or it's intractable to compute. We'll look at how to make use of importance sampling to draw sample, or to draw sample such that we can model this particular complicated probability distribution. We'll use importance sampling, of course, to do this, where we can simply rewrite this particular marginal or conditional probability distribution into this form over here, where the numerator is simply the joint probability of all the random variables given that x2 and x3 are observed to be taking a state of 1, divided by a normalizer here. So this normalizer here requires us to marginalize away all the nuisance random variable, which we can see that this can be denoted as a set of query nodes xf and a set of evidence nodes which we denote as xe. This is following the representation that we have seen in our earlier lecture, divided by the normalizing constant, which is the marginal probability over all the evidence nodes over here. So in this case, we are going to pretend that this particular normalizing constant is very difficult to evaluate because it involves a sum or marginalization over many random variables which we don't want to evaluate. Hence, we will let the numerator over here, the joint probability distribution given by the graphical model, to be our target distribution. So this is our P tilde. And the question now is that what should we use as our proposal distribution? So one possibility of a proposal distribution where there's actually no fixed way of selecting a proposal distribution. You can actually use any proposal distribution by taking any slice of the probability distribution table that is given together with the graphical model as your proposal distribution. So one choice over here would be to get the proposal distribution to be the marginal probability of x1 multiplied by x4 conditional upon x3 equals to 1 multiplied by x5 conditional upon x2 equals to 1. So we can see that these 3 probability distribution here, they are a lot simpler to draw sample from as compared to the original target distribution, which is this whole distribution over here. So it's not going to be easy for us to draw the samples over this proposer or this particular target distribution, which we denote as P tilde over here, which is given by the joint distribution of every single random variable and all these tables over here. Now, once we have defined the proposer distribution, we'll proceed on to answer the question on how to draw samples from the proposer distribution. So we need to draw x1 from the marginal probability of p of x1, and then we need to draw the samples of x4 from this conditional probability, as well as x5 from this particular conditional probability over here. So the idea here is very simple. We will simply look at the probability distribution of our proposer distribution one by one, because it can be factorized into this version over here. So we'll first look at the marginal probability of x1, which is given by this guy over here. x1, there's a 0.6 chance that it will be equals to 0 and 0.4 chance that it will be equals to 1. So what we'll do first would be to uniformly draw a sample within 0 to 1, and then we are going to call this sample, we are going to call this number n. So in the case where n is more than 0.6, then we will say that x1 equals to a state of 1. And in the case where this number is lesser than 0.6, we will say that x1 takes a state of 0. We'll do the same for x4. So we can see that x4 is drawn from the conditional probability of x4 conditional upon x3 equals to 1. And that would be equivalent to this particular probability distribution table here, where the conditional probability corresponds to this probability distribution table over here, where we simply just take the slice of the conditional probability of x4 conditional upon x3 to be equals to 1 from the given probability table over here. So in this case here, what it means is that we are going to take this particular slice where it corresponds to x3 taking a state of 1, and that is equivalent to x4 probability of 0.4 to be in the state of 0, as well as 0.6 in the state of 1. And we'll do the same thing. We'll draw a random number within the range of 0 to 1, which we denote as n. And if n is lesser than 0.4, then x4 will take a state of 0. And if it is more than 0.4, it will take a state of 1. We'll do the similar thing to draw a sample of x5 from the conditional probability of x5 conditional upon x2 equals to 1. Now, once we have drawn enough samples from the proposer distribution, we'll evaluate the weight of every single sample, normalized by the sum of the weights of all the samples that is drawn in the important sampling algorithm. So this is given by WL equals to R tilde L divided by sum of R tilde M. And we saw in the earlier slide that this can be easily computed from the unnormalized target distribution as well as the proposer distribution of Q. Now, suppose that the first set of sample that we have drawn, it's in the state of x1 equals to 0, x4 equals to 1, x5 equals to 1. So this means that in the first step, in the first iteration that we are going to draw the sample, we'll consider the sample of x1, x4, x5 as one set of sample. So every time we draw a sample, we are going to draw a set of 3 samples from x1, x4, and x5 respectively, and with one single random number that is being drawn over here. Now, for each set of sample of x1, x4, and x5 that is obtained, we will evaluate the probability values from the unnormalized target distribution given by this equation over here, where we are going to suppose that x1, x4, and x5 that we have drawn equals to state of 0, 1, and 1. We're going to substitute this back into the unnormalized target distribution which is given by the factorization of this the expression over here, the full expression over here that's given by our Bayesian network that is shown in the previous slide. And we can easily compute the probability value of all these terms by looking up this probability table that is given to us together with the Bayesian network, and we'll compute this value that corresponds to the unnormalized target distribution over this set of sample that is drawn for x1, x4 and x5. Then the next thing that we will do would be on the same set of sample, we will compute the probability value over the target distribution. Now the expression of the proposal distribution is given by this expression over here, which is what we have decided as our proposal distribution in the earlier slide. And we can easily also compute the probability value from here by simply evaluating the probability of each one of these terms from the probability distribution table that is given in this proposal distribution here, which is actually the slices of all the entries of the whole graphical model, or all the probability distribution tables that was given to us in the together with the graphical model. And now once we have evaluated the probability value for both the unnormalized target distribution as well as the proposal distribution, we can compute the importance weight for the L sample given by the division of these two probability values. And after we have computed the importance weight for all the L samples, we can then compute the normalizer for this importance weight, which is simply given by all the sum of the importance weight of all the samples that we have drawn. And then we can compute finally we can compute the importance weights for every one of the sample that we have drawn. Now, after we have computed all the weights and have drawn all the samples from the proposal distribution, the final thing that we can do would be to compute the probability table for the target distribution that we are interested in. So this would be the probability distribution that we are interested in. That's the marginal probability of x1, x4 and x5 conditioned upon x2 equals to 1 as well as x3 equals to 1. So what this means is that we have to fill up the table of this marginal probability table over x1, x4 and x5 over all the combinations of this marginal probability distribution over here. So here we can easily compute, for example, x1 equals to 0, x4 equals to 0, x5 equals to 0, condition upon x2 equals to 1 and x3 equals to 1. That would be equals to the number of times that we observe that the samples, the set of samples are drawn taking the state of x1 equals to 0, x4 equals to 0 and x5 equals to 0, multiplied by the importance weight for every sample, the respective sample that we have computed in the previous step, and we'll sum them all together. So this is equivalent to the weighted sum of all the samples that we observe to be taking the state of 0, 0, 0, and we'll have to ensure that this is a proper probability value. That means that all this should sum out to 1. All this probability value should sum out to 1. Hence, we are going to divide it. We are going to normalize it with the sum of all the importance weight values. And in summary, we will be able to compute the conditional probability of a set of query nodes conditioned upon a set of evidence nodes by this particular equation over here, that is reliant on the importance sampling, or the samples that we have drawn from the proposal distribution weighted by the importance sample. Now, the sampling algorithm can also be applied to the expectation maximization algorithm, where we simply use this expectation maximization algorithm to solve for the case where we have a set of observed random variables as well as a set of latent random variables and unknown parameters for the distribution. So we saw in the previous two lectures that in this case over here, where we have a concurrent latent set of random variable as well as our unknown parameters over here, we have to use the alternating EM algorithm, where we do an expectation step on the posterior of the latent random variables, and then we'll maximize over the unknown parameters in the maximization step. And in the EM algorithm, we also saw that this is important to compute this posterior probability distribution. So we saw that just by a simple difference, a very simple difference, that the latent random variables are linked to each other in the Markov chain, we'll end up with a very complicated forward-backward algorithm to compute this posterior distribution. And it could be the case that it is much more complicated than just a simple first-order Markov chain, where it will render this particular posterior distribution intractable to be computed analytically. So one way to get around this would be to make use of the sampling algorithm, which will allow us to directly evaluate the integration of the expectation on which is given by this term over here, where we'll simply approximate this particular integral sign with the samples, with all the samples that is drawn under this posterior distribution, and we'll make this our target distribution since we are unable to compute it directly. So this, as a result, this expression of Q over here would be equivalent to the summation, the average over the log probability of the complete likelihood over all the samples that are drawn of the latent random variable drawn over the posterior distribution of PZ condition upon X and theta O, which is here X as our target distribution. And this is very complicated to evaluate analytically. We'll do the same optimization over all the samples that is drawn in this way over all the unknown parameters, and we'll iterate. We'll do the alternating steps between the expectation and maximization, when now the expectation algorithm involves the sampling over the target distribution. And this particular procedure here is what we call the Monte Carlo expectation maximization algorithm. So we saw earlier that one of the biggest limitations of the importance sampling algorithm is that when there is a huge mismatch between the proposer and the target distribution, we will end up with a set of samples that are unable to model the target distribution well. And we'll see how we can overcome this particular problem using the Markov chain Monte Carlo algorithm. And in short, MCMC is a strategy for generating sample while ensuring that we can explore the whole state space using the Markov chain. And the Markov chain is constructed. We'll see that it's constructed in such a way that we will ensure that we will spend more time in sampling the most important region. That is to say that just now we saw that suppose we have a bimodal distribution that looks something like this. In a case where we use importance sampling and a wrong proposer distribution, we might end up with very few samples in the important area with a high probability. And now in the MCMC algorithm, we will design a Markov chain such that we will spend more time in sampling these regions with higher probability. In particular, we will construct the Markov chain such that the sample mimics the one that is drawn directly from the target distribution. So the biggest difference between the MCMC algorithms and the importance sampling and rejection samplings that we have saw earlier is that the MCMC sampling, instead of using a fixed proposer distribution, it features an adaptive proposer. So instead of a Q prime, which we use to draw the proposer sample at the particular time step, we use Qx prime condition upon X, where X prime is the new state that we want to sample currently, and x is the previous sample. So as x changes, that means that as the sample changes at every iteration, the proposal distribution also changes with the sample that was drawn previously. And here's an example, or here's an illustration of importance sampling versus the MCMC sampling. So we saw that if the target distribution over here, denoted by P of x, is a bimodal distribution, in the case of importance sampling, suppose that we have the proposal distribution as Q over here, which is denoted by this red Gaussian distribution, and if we were to choose it in to be at this particular location, our proposal distribution, what this means is that we'll end up drawing samples that is only able to model this particular region over here that is covered by our proposal distribution. So what happens is that all these regions that are not covered by our proposal distribution will not have any samples at all. As a result, we will not be able to draw sufficient samples, or samples that can represent our target distribution in a high fidelity. So in the case of the MCMC sampling, instead of using a fixed proposal distribution, we are going to use an adaptive proposal distribution here. Now, we'll look at the same example where the target distribution is a bimodal distribution given by the black curve over here. And instead of using a fixed proposal distribution denoted by Qx, we'll use a proposal distribution that is conditioned upon the sample that was drawn in the previous step, which is denoted as x. And we'll draw the current sample x prime, where from this particular adaptive proposal distribution. So in other words, we are going to draw x prime directly from the adaptive proposal distribution that is conditioned upon the previous sample that was drawn. And here's an illustration. Suppose that we begin with the same proposal distribution as our importance sampling, shown by the red curve over here. What we are going to do here is that we are going to draw, and suppose that the first sample that we drawn from this particular, that we are given, it's x1 over here, that corresponds to this, the peak of this proposal distribution denoted by the red curve. And we are going to draw the next sample. So what happens here is that we are going to use this adaptive proposal where x2, the sample distribution of the next sample, is going to be conditioned upon the current sample, which is x1 over here. This means that I'm going to draw x2 from this proposal distribution, which is denoted by the red curve. And suppose that we are drawing this particular sample over here, and which we denote as x2. We are going to now draw another sample of x3 in the next time step from the proposal distribution of x3 conditioned upon x2, which was our previous sample drawn from the red curve over here. So in other words, we are going to form a new Gaussian distribution, which is denoted by the green curve over here as our next proposal distribution. And suppose that we are going to draw x3 from this particular proposal distribution represented by the green curve. We are going to draw the next sample, which is x4, from this particular proposal distribution that is conditioned upon x3, as shown by the blue curve over here. So here we are going to, in other words, we are going to draw x4 from this Q, which is conditioned upon x3 over here. And what's interesting here in this illustration is that we can see that our proposal distribution is adaptive. This means that it moves around the distribution space. It moves around the whole state space. And as a result, as we continue to sample more and more samples, we are almost guaranteed that this is going to move around such that in a way such that we are going to cover all the state space, such that we will be able to draw enough sample to represent the target distribution. So before I go into the proof on why Metropolis-Hasting algorithm works, let me first introduce this algorithm, which is one form of the MCMC sampling. So we'll first initialize the sample, which we call x0. So this could be anywhere in the state space of the random variable of x. Note that x here could be a set of random variable. It need not be just one random variable. And our objective here is to draw n number of samples from the target distribution that is denoted by p tilde of x. This is the unnormalized form of the target distribution. We'll first draw a sample which we denote as u from a uniform distribution between 0 to 1. And then the next thing to do would be to draw a sample which we denote as x prime from the proposal distribution conditioned upon the sample that was drawn in the previous time step or previous iteration. And once we have drawn the sample from this proposal distribution, which we denote as x prime, we'll compare u with the acceptance probability, which is denoted by a over here, where a is actually a function of the current sample x prime and the previous sample of xi. So we'll compute a using this equation over here, which is given by the mean of 1 and the ratio of these two probabilities over here. So we'll take the unnormalized probability evaluated at x prime, the current sample, multiplied by the proposal distribution of the previous sample conditioned upon the current sample, and divided by the unnormalized target distribution evaluated at the previous sample, multiplied by the proposal distribution, the probability of the proposal distribution evaluated at the current sample conditioned upon the previous sample. And we'll accept this new sample over here if u is lesser than the acceptance probability, or otherwise we'll discard this new sample and simply replace it with a duplicate copy of the previous sample. Here's an example to illustrate the Metropolis-Hasting algorithm. Our goal is to sample from a bimodal distribution px, which is also our target distribution as shown as the black curve over here. So let us let the adaptive proposal distribution, this is our proposal distribution, be a Gaussian centered upon x, which is the previous sample that is drawn from the distribution. And here we'll evaluate the acceptance probability using this formulation over here, where we know that this unnormalized version of the target distribution is easy to compute, as well as since Q here is just a Gaussian distribution centered upon x, where what this means is that the mean of the Gaussian distribution is on x, and it will have a fixed variance which we have to predefine as our hyperparameter, and we'll be able to compute this Q, the proposal distribution, at the previous sample conditioned upon the current sample, as well as the other way around, as shown in this equation. So we'll initialize x0 to be anywhere on the state space of the random variable or the set of random variables of x. Then the next thing that we do is to draw a sample from the proposal distribution, which is given by this equation over here. It's a Gaussian that is centered upon the first initialized random variable denoted as x0 over here. So this is denoted by the red curve over here. And what we are doing here is that we are sampling x1 from this particular proposal distribution. Then suppose that we accepted the first sample that we sampled from Q x1 condition upon x0, where we draw a sample here of x1. Suppose that we have already accepted this particular sample because it passed the criteria that u that is sampled from a uniform distribution of 0 to 1 is lesser than the acceptance probability. We'll go on to draw the second sample denoted by x2 over here. And this would be drawn based on the proposal distribution that is centered upon x1, the first sample that was drawn here, as shown as this red curve over here. And what it means is that we're going to draw another sample from this proposal distribution. And now suppose that, again, we fulfill this particular condition over here, where u is lesser than the acceptance probability. We'll continue to draw another sample under the proposal distribution condition upon x2. So what it means is that we are going to draw x3 from this. And now suppose that we draw this, but we reject this particular sample. We reject it because this value over here is lesser than 1 and this value here is more than 1. Hence, if we plug this into this particular equation over here, we'll see that these values here are very close to 0, and we are taking the mean of 1 or this value which is very close to 0, and hence we select this value as our acceptance condition. But in this case here, it's unlikely that u is going to be lesser than these values that is already close to 0. Hence, we reject the sample. And once we rejected the sample, we will ignore that sample, that is x3 sampled from this adaptive proposal distribution. Instead, we'll set x3 to be the same as x2. And in this case here, note that we are not simply discarding x3, but we are creating a duplicate copy of x2 over here. And we'll do this until finally we get enough samples. So one important thing of the MCMC sampling algorithm is that we need to take note of the burn-in period. So as noted earlier on, that the initialization of the samples is based on any random selection of any samples in the whole state space. Suppose that this is our target distribution, and we will randomly select one random variable in the whole of the state space in order to represent this particular first sample. So since we do not know where exactly is the range of the that this particular target distribution covers, we might end up to select one random sample, the first random sample, to be very far away from the target distribution with high probability values, which means that we might end up selecting one sample from here, and it might actually take a long time before we before our adaptive proposal distribution shift to cover the space of the target distribution with sufficiently high probability value. And so as a result, we need to discard the first x number of random samples that we sample from the MCMC or Metropolis-Hasting algorithm. And the 2D example is here, where we can see that the Gaussian distribution here, it has a sufficiently high probability in this region, and we might but in this case, the 2D search space over here, the 2D state space x1 and x2, could be anywhere in the region, and we do not know, since we do not have any idea of where this target distribution is going to lie. And as a result of random selection of the first sample, we might select a sample that is very far away from the probability distribution, and it will take some time for the proposal distribution to move to the target distribution with high probability value, and consequently the first few samples that we sample over here are not going to be important, are not going to tell us the true distribution of the target distribution. As a result, we will call this segment of the initial samples as the burn-in period, where we will discard all these values. And unfortunately, there is no way to figure out how many samples are there that in the burn-in period. So typically, we will just discard the first 1,000 or so samples.